didn't quite finish what I wanted to do last time. So we're going to talk about some terminology. It's not too critical, but it's nice to know what words mean. And so there's a few points in the next few weeks where we're going to talk about optimization. And there's some specific terminology we want to have available to us. And so if you hear certain words, you're like, I know what that means. So we have terminology for points. And in particular, I'm thinking I have this collection of points. So here it's the green points. It's a collection of points. Here it's in a two-dimensional space. But oftentimes you can be in any dimension. For convenience of drawing, we put 2 dimensions. And you'll notice that there are some points which are dashed or are dotted on the edge. That indicates we don't include those points. Solid means we do include the points. So oftentimes we want to talk about, well, what kind of points are these? We want to give names to things. So here are some names that you might encounter. So an interior point just says, I'm on the inside. So interior is like on the inside. Like an interior decorator, they decorate the inside. So what it means is if I'm an interior point, everything nearby is an interior point. So in other words, I can put a small circle around there, and lo and behold, everything in that small circle is on the inside. So that's what we mean by the interior. Now an exterior point means something on the outside, like an exterior decorator. Although I don't think they have those, but okay. So like that's an exterior point, because if I look around it, everything around it is also on the outside. So when we talk about the word small ball, that's just a fancy way of saying really close. And so, all right, what's a boundary? Well, a boundary point is a case where if I put a small ball, it doesn't matter how small I put it, there are some points on the outside and some points on the inside. Now you notice that it's possible to be a boundary point and not be in your set, and it's possible to be a boundary point and be in your set. So for example, here's a boundary point which is in your set. Here's one which is not. What's an open set? Well, an open set just means that everything's on the interior. Okay, so this is not an open set because you'll notice this is not an interior point. But on the other hand, if we had done this, where we didn't include anything on the exterior, and we had said, hey, how about this? Then the answer is that is an open set. Now, the easiest open set, well, there's 2 super easy open sets. One is everything. So everything forms an open set. Because if you put a small ball around it, well, that includes the points are in there as well. They're still on the inside. Now, the other easy empty set, this is just a fun trivia. It's called, the other easy open set is the empty set, which is often denoted with this symbol. I don't know if anyone's ever encountered the empty set before in their math courses. Has anybody seen it before? A few people have. Have you seen this symbol before? Do you know where it comes from? A lot of people think it's the Greek alphabet, like it's the phi. But no, it's not. It's the Norwegian alphabet. And it's an So, you know. If you're talking about the empty set, you're like, yeah, that's right, the empty set, exactly, good. All right. Well, you know, math, we come from a lot of diverse cultures coming together to form this wonderful thing called math. All right, what's a closed set? Well, every boundary point of the set is in the set. All right, so for an example, if I include the boundary, so even just that circle is a closed set, but if we fill the circle with points on the inside, that's also a closed set. And this set we started with is neither open or closed, because it's not an open set because of these points on the boundary which are in your set, and it's not a closed set because these points on the boundary are not on the inside. So, all right. Well, what's important about closed sets? Well, okay. There's a second type of thing which is bounded. So a bounded set just means I'm not too big. In other words, I don't have parts heading off towards infinity. That's what a bounded set is. And we're going to talk about the notion of being closed and bounded. And the reason that closed and bounded are important, and I'll say this again later on, is because they have this beautiful property that if you have a sequence of points in your set, they go somewhere. And where they go is in your set. And that's what makes closed bounded sets so nice. And if you want to know more about this, there's a lovely topic, topology in particular, but really any basic analysis course will do that. All right, so on to today's topic, which will be a little bit of a refresher because you probably saw this in Calc 1. Let's talk about why is division by 0 bad? Okay, do you remember the answer to this? Why can't you divide by 0? What's so bad about it? It's what? It's ambiguous. Ooh, somebody remembers. Okay, so what do we have? Well, A divided by B is equal to C means that A is B times C. Pretty much everybody agrees to that. That's what it means to be able to break things into equal-sized parts. So let's divide by 0 and go through what happens. So A over 0 is C if A is 0 times C, but 0 is a fantastic number. 0 times anything is 0. And so we now get two cases. If A is not 0, you end up in an impossible situation. It just can't be done. Because then you have something which is 0, namely the value A. But you also know A is not 0. Okay, well, something can't be 0 and not 0 simultaneously. So that's why we say it's impossible. And the more subtle reason is if A equals 0, and that's ambiguous. Now you might say, well, wait a second, but it satisfies the relationship. It does, but for what C? That's the problem. See, it could satisfy it for any C. So that's why we say there's ambiguity. It's not clear what the right choice is. So we need to have a way to resolve. All right. So if we don't know what 0 over 0 is, we ask ourselves, what should it be? So that seems like a reasonable thing to do. I don't know what the value is because it's an ambiguous thing, but I can ask what it should be. Now the problem is if I just take it in isolation and I say 0 over 0, it doesn't mean anything. But maybe 0 over 0 is showing up in terms of a computation, and I can start saying, well, it's related to things close by. So here's the beautiful idea in calculus is about limits. And they say, limits are asking the question, what should happen? So I want to talk about the limit of the function. And so I have this idea of saying, what's happening as I'm getting near my point? So I have my function, and we're going to do a multivariable function, because we're multivariable people now. We're taking the limit as x and y gets close to AB. So I have some point, and xy is getting close to that point. And I'm saying, what's happening to it? So this limit is saying what should happen. Well, maybe it's getting close to a particular value, and maybe it's not. But the key thing is to say, what's happening nearby? So that's how limits are working. They're looking, what's nearby, what's that behavior, and based on that behavior I'm seeing, what should the answer be? Now, there's a couple things to note here. You'll see that we use a word several times, namely the idea of close and close. Things are close. Now, close is really talking about distance. So I'm saying I want the distance between things to be small. Now, there's a formal definition of limits, and we may have mentioned this in passing. Oftentimes in Calc 1, we just fly past this. But it says the following. So for every epsilon greater than 0, there's a delta greater than 0, so that if the distance between the point x, y, and AB is less than delta, then the distance between f of x, y, and L is less than epsilon. Now you'll see that really this absolute value, this should be thought of as a distance in all cases. Whenever we see the absolute value signs, think of it as distance. And we have two of them, because there's two occurrences of close. The inputs are close, the outputs are close. Well, how close? I just want to make sure this means very close. So in other words, epsilon greater than 0 says, I want to make sure my output is very, very close to where I think it should be. And then there's a gain. All right, no matter what epsilon you give me, I say, I can guarantee that's possible. You just have to make sure delta is sufficiently small. And it leads into a very, depending upon your perspective, exciting or not exciting game. Say, you give me an epsilon, I'll give you a delta. Now, it's a great game to play, and there's some wonderful classes where you can take, and you'll get to play this game, but not this class. So this will be the last time we mention the formal definition of limits. But it's nice to know that there is actual, there's something underlying calculus that says there's a reason things work. And this is why. And if you say, well, but this, one of the things I've noticed over the years is that students sort of say, this formal definition is really weird to get a handle on, but it's really just saying the same thing as this informal definition. I'm close. I'm close. Now, a few simple things to say about limits is that they're very intuitive. So here are some examples. Suppose I know that this function f of xy goes to L, and g of xy goes to m. Then what happens is if I add the two together, so in other words, f of xy plus g of xy, and I take that limit, well, it goes to L plus m. So in other words, f is getting close to L, and g is getting close to m. So f plus g is getting close to L plus m. And that's almost the whole proof. There's a few little epsilons and deltas to chase, but they're not very hard. Similarly, f times g is getting close to L times m. And f over g, well, that goes to L over m, assuming, of course, m is not 0. Now, what if m is 0? What happens? Well, the answer is more work. Usually. It's possible that L is not 0, and then there's almost no work at all to do. And one other nice property is if I have a continuous function, then I have that the limit of xy going to ab of h of f of xy is h of L. In other words, limits pass in and out of continuous functions, which is why we like continuous functions. Continuous functions and limits get along very, very well, as we are about to discover. All right, so let's talk about continuity. So what does it mean to be continuous? Do you remember the definition of continuity? There's the informal definition that you might remember from high school. It says, look, I'm continuous if I don't have to lift my pen or lift my pencil. I guess nowadays it's I don't have to lift my stylus because, I don't know if people use pens and pencils anymore. But there's a more formal definition. And what is it? It says that a function is continuous if the following is true. If I look at the limit as I approach a point, so in our case, again, multivariable, but it doesn't really matter. It's the same no matter what setting you're in. So I'm approaching my point for my function, and I say, what should happen? That's the limit. And then I compare it to what the function actually says happens. That's f of ab. So if the limit as you approach your point matches what the point says at that point, you're continuous. So in other words, a continuous function can be said it's a function without any surprises. What does happen is what should happen. So that's really convenient. All right, well, let's talk about examples of continuous functions. The most famous example are polynomials. Now, we're multivariable calculus now, so our polynomials can be a little bit more interesting in that they can involve multiple variables. So, for instance, I could have x to the 7th y cubed plus 6xy squared. That's a polynomial. So it's essentially just combinations of powers of x and y. But we're going to assume right now the whole positive numbers. And that's 2 dimensions. Of course, you can have multivariable, meaning 3 variables. So we could go up and say, hey, how about like x to the 7th y cubed z squared plus x y to the 100. Yes, polynomial. So, okay, polynomials are nice, and polynomials have no surprises. In fact, it's one of the easiest exercises to prove, not for our class, but for a different class, that polynomials have no surprises. What are some other nice continuous functions? Sine, cosine, arctangent, had to be mentioned at some point, exponential. These are all wonderful and continuous functions. When I say the exponential function, that means e to something. So the way to remember that is that exponential starts with e. All right. So I can now do things such as sine of, say, x cubed plus 7y, and that's continuous. Now, how do I know that's continuous? Well, it's because I know a couple things. I know that x cubed plus 7y, that's continuous. Why? It's polynomial. And then I can say, well, if I do sine of that, that's continuous. And that comes back to this idea we talked about at the very bottom that says, hey, in this case, my h is the sine function. So I'm thinking that it's a sine of a continuous function. So I can pass the limit through, no surprises. What should happen is what does happen. And, well, I would just not be doing my job if I didn't write down an arctangent of something. Arctangent of x plus y. What a great function. Perhaps we'll see more functions like that in the future. Now there's other things. That we have functions like tangent, log, square roots. These are continuous functions when you stay in their domains. Now what I mean by that is where they're defined. So tangent isn't defined everywhere. It has some problems. It has some asymptotes. Log isn't defined everywhere. So you can have a function. So for example, a function like, let's see, log of x squared plus y squared. Well, what does that look like? Is it defined everywhere? From last time, what's the domain of this function? Well, to be continuous, or sorry, to exist, I need to make sure I take log of something which is not negative. Okay, x squared plus y squared can't be negative. And it can't be 0. When does x squared plus y squared equal 0? At the origin, at 0, 0. So this is not defined at 0, 0. But away from 0, 0 is perfectly fine. So what does it look like? Well, it looks like something like a black hole. Because what's happening is it's going down as you head in. So in other words, it's collapsing because log approaches negative infinity when its input is approaching 0. So as you approach towards this point, 0, 0, you're heading off towards negative infinity. Now, the goal for today, and it's a good goal, is we want to talk about evaluating limits. So we're going to have a couple of strategies, and we want to outline them. And so there's going to be more or less 4 strategies we're going to talk about. So our first strategy relates to continuous functions. And because continuous functions are really useful. Now there's a note on the top here that says it's easy to make continuous functions by putting them together. And here's our strategy. If your function is continuous, just plug it in. And you're done. Now you might say, whoa, that seems really easy. I like this strategy. And you're right. You do like this strategy, and it's the one you should hope for. But why does it work? It works because when you have a continuous function, what should happen is what does happen. It's the definition of continuity coming to help you. And so when you have something which is continuous, you say, let me plug it in. So as a first rule, if you see a limit, before you panic, or after your panic attack subsides, one of those two, check to see what happens at your limit point. All right. Well, assuming, of course, you have a continuous function. So let's find the following. Limit as xy approaches the point 1, 1 of x to the 7th y squared plus sine of cosine y plus y squared x plus x times e to the y divided by x squared plus 3 arctangent of x plus y plus 4 secant squared of xy. Now, it looks complicated, but that's to misdirect us. It's to make us think, it's a complicated question. When really we should say, wait a second, let's use our tools. First question, is it continuous? Well, if you're not sure, just sort of think about how you go about seeing things are continuous. The idea is you have some basic building blocks, so like polynomials, sine, cosine, arctangent, exponential, even some square roots, tangents, logs. We can even throw secant in there. Those are our building blocks. And then you have ways to combine in things like adding and multiplying, dividing, composing. Composing means putting one function inside of another function. So you have building blocks of continuous functions, and you have ways to put them together. It's the same thing when we talk about rules for differentiation. You have a couple of basic functions that you know the derivatives of, then you have a few rules, and once you have those two things, you can put things and take derivatives of almost anything that you'll encounter. So in our case, let's sort of go through and say, well, x to the 7th y squared is continuous because it's polynomial. Cosine y is continuous. Y squared x is polynomial. I add continuous functions. It's continuous. I put a continuous function into a continuous function. Continuous. X is continuous. E to the y is continuous. It's the exponential. So if I multiply them, they're continuous. If I add them up, they're continuous. Now, normally we don't do this, but it's good to sort of say, okay, I can see why putting things together gives me a continuous function. Same thing downstairs. X squared is continuous, 3 arctangent of x plus y. Arctangent, lovely function, no problems. We love arctangent. Now, secant squared might make us just a little tiny bit nervous. Why might secant squared make us nervous? Yeah, secant squared actually is not defined everywhere. There are places that you can plug in and you get an undefined value. So we have to check. Let's just check for secant squared. We're plugging in 1, 1. So we have secant squared of 1. Is that an okay value? Well, our bad values are things like pi halves and negative pi halves, or anything off by a multiple of pi. Okay, good. Secant squared of 1 is okay. So our answer to this very complicated question is plug in 1. So we just plug in 1. 1 to the 7th times 1 squared? 1. Plus sine of cosine of 1 plus 1 squared times 1, which is 1, plus 1 times e to the 1, which is e, divided by 1, plus 3 arctangent of 1 plus 1, which is arctangent of 2, plus 4 secant squared of 1. All right. And now, after this, what do? Yeah, we're done. We had a continuous function, so we used the properties of continuous function to say, plug it in, and if you get something you like, you're done. You're done. Okay, so that's strategy number 1. Look for continuous functions. Now, it doesn't always work because you might get things which are 0 over 0, so we have to have other strategies. That's okay. We're not done yet. We have more strategies to come. All right, so here we go. Let's see if we can get this on the screen. Okay, strategy number 2. Good. So strategy number 2 is actually not really finding the answer to a limit. It's about saying, maybe we can say the limit doesn't work. It's broken, doesn't exist. Now, how does the strategy work? It says, I'm trying to find what the answer should be as I get close. Well, maybe there's more than one way to get close. And depending upon which way I choose, I'll get a slightly different answer. Now, the problem is, you can't get two different answers. If there's a limit, you always have to get the same answer regardless of how you get close. So, what we'll do is we'll look at all the ways we can get close, or maybe just a few ways. If we get different answers, no limit, doesn't exist, and we're done. Oh, that's great. So let's talk about sort of where does this analogous to? Well, when we took Calc 1 a while back, oh, we were so young and innocent back then. But we did something. Do you remember what we did? What? One-sided limits. We said, hey, I want to know what's happening at that point. So what I'm going to do is I'm going to look from the different sides. Because there's really only two ways to approach that point. Either approach from the left or from the right. That's it. Those are the only two ways to approach. And so one of the ways you had is you said, well, if I want to understand a limit, I can say what's happening on the right-hand side, what's happening on the left-hand side, and then do they agree? And if they agree, the limit exists. Now, that's in our old single variable mindset. We're multivariable now. Here's our new picture. So now, I'm not on a line, I'm on the plane. And I want to approach that point. Well, how many different ways can I approach that point? Sorry, what?
Bajillion.
A bajillion? That seems like an imaginary made-up number. Let's talk about a couple of different ways you could do it. What are some simple ways we could do it? Well, we can still approach from the left and the right. In very faint colors, apparently. All right. What else could we do? Yeah. We can approach from the two sides. Whatever that means. Up, down. Okay, so left, right, up and down. Is that it? Yeah, maybe from an angle. Maybe we could approach from those directions. Okay, so now we were approaching from lots of different ways. Is that all? That's right. It's like we're in an infomercial. But wait, there's more. Act now, and you too can approach from a different direction. Now, what do I mean? Well, so far, I've been pointing from straight lines. Well, maybe you've had a little bit too much root beer, and you have sugar, and you're just going all over the place. And so instead of approaching on a straight line, you're just wiggling back and forth. Is that okay? Yeah! Look, you can approach it any way you like. It doesn't have to be on a straight line. It doesn't. No, you could even do things like spiral in. Is that okay? Yeah, absolutely. As long as you get there. So you're allowed the freedom to approach it any way you want. Now here's the catch. This strategy has severe limitations. I've already mentioned, I'm going to say it again. There's a little bit of a warning here. This is only useful to show limits don't exist. So be careful about what your conclusion is. All right, let's do some examples, because I like this one. So find the limit as xy goes to 0, 0, x squared minus y squared over x squared plus y squared. What do you get? Well, of course, our first strategy is plug in 0 and 0. And if we do that, we get 0 over 0, which means more work. More work. 0 over 0, got to do more work. That shouldn't be a sad thing. That should be like a yes! Woo! Get to do some more. Loving it. Okay, so we're going to be in this mindset. Strategy number 2. All right, so here I have my axes, and I have my point, which happens to be the origin. It's a very convenient point to look at. And let's talk about some ways we can approach. What are some ways I can approach? Sorry, for where? From the right. All right, so we're going to talk about from the right. In fact, I'll talk about going from a horizontal. We'll do right and left simultaneously. Now, here's the key. Here's how you should be thinking of it. Right now, we're talking about this limit, and we have two things that can change, both x and y. When I talk about coming in from the right or the left or along some other strange direction, I'm saying let's simplify it down to something more one-dimensional. And that's what's going on, is we're moving it to a one-dimensional thing. Why? Well, because in one dimension, we have tools. And we can use our one-dimensional tools. Okay, so let's talk about what does it mean? Well, a typical point on our way that we approach looks like t comma 0. Yes, because I'm on the x-axis, so my y value is 0. So, as I do the horizontal direction, what I can really say is that it becomes a limit, not as x and y approaches 0 and 0, but it becomes a limit as t goes to 0. And now what happens is everywhere where I see an x, I'm going to put in a t. And everywhere where I see a y, I'm going to put in a 0. So t squared minus 0 squared over t squared plus 0 squared. Well, that becomes a limit. T goes to 0 of what? Of 1. Well, what's that limit? It's 1. Okay, so what's our answer? There is no answer yet. We just say, if we come in this direction, we get 1. We haven't proven very much. We actually have proven a little tiny nugget. The little tiny nugget we've just proven is, if there is a limit, what does the answer have to be? The answer has to be 1. Because our answer has to be always consistent. Have we proven the limit exists yet? Not the original limit, no. We've said when we've limited ourselves to the horizontal direction, yes, we know the limit exists. However, perhaps there's a different way. What's a different way we could approach? Vertical. Yeah. All right. Now, if I'm vertical, what does a typical thing look like? 0 comma t. Okay, so for vertical, what do we have? Well, again, it becomes a one-dimensional limit. This limit as t goes to 0. And essentially, on a side note, what you can think of what we're doing is we're parameterizing a curve and saying what's happening on that curve. So everywhere where we see an x now, we're going to put 0. And everywhere we see a y, we're going to put t. So 0 squared minus t squared over 0 squared plus t squared, which becomes the limit as t goes to 0 of what? Negative 1, which is negative 1. Okay, so from a horizontal direction, we said the answer should be 1. From a vertical direction, we said the answer should be negative 1. So do we average? 0? No, we don't average. What do we say? Limit does not exist. Limit does not exist. Good. Because 1 and negative 1 are not the same. All right, 1 down. We'll see if we can do a few more. Okay, the next one. Sort of a similar one. So let's try it. Okay, so limit as xy goes to 0, 0 of the quantity x times y divided by the quantity of x squared plus y squared. So again, if you plugged in 0 and 0 to start, you'd see that we'd get 0 over 0. Bad news. That's okay. It's not bad news. It's great news. More work. All right, so let's go through and do what we did last time. From a horizontal direction, well, that, remember, was t comma 0. So that becomes the limit, t goes to 0, of 0 times t over t squared plus 0 squared, which is the limit as t goes to 0 of what? Of 0, which is 0. All right. Well, while if we go in a vertical direction, and in that case we have 0 comma t, vertical would be the limit as t goes to 0 of t times 0 over 0 squared plus t squared, which is the limit as t goes to 0 of what? 0, which is 0. They agree. What's our conclusion? It might exist. If it does exist, the answer is 0. Does it exist? We don't know. We can't prove it. All right. Well, so there's two options. Either start trying to prove that the limit is 0, or try a different direction. Which should we do? Try a different direction. That sounds pretty convincing. Which way do you want to come?
Sine wave in.
Let's not be fancy yet. We'll say fancy for the next one. Diagonal sounds great. Coming in from a diagonal. So if I'm on a diagonal, what does a typical point look like? Think of the parameterization. T comma t. That's right. Okay. So this becomes the limit as t goes to 0. So everywhere I see x, I put a t. Everywhere I see y, I put a t. I'll have t times t, which is t squared, divided by t squared plus t squared. Well, that's the limit as t goes to 0 of what? 1/2. So our answer of that limit is 1/2. So now what do we conclude? Does not exist. Good. All right. So sometimes you have to try a few things. All right, one last one, and then we'll move on to our next strategy. It looks almost the same. Find the limit as xy goes to 0, 0 of x squared y divided by x to the fourth plus y squared. Okay. Any guesses before we start? You're probably going to guess doesn't exist. Let's see if I can shake that a little bit. I think this one's going to be a little bit interesting. To be fair, I've done this one before. It's a nice one. All right. If you plug in 0, 0, what happens? You get 0 over 0, meaning more work. Ah, good times. All right. Which way should we do first? Diagonal? Come on. Okay. Let's save diagonal for a second. How about let's go straight up and down. And then I'll do diagonal next. Just bear with me. Straight up and down. If I'm straight up and down, I tend to look like something of the form 0 comma t. So, from a vertical direction, I get the limit as xy goes to 0, 0. I don't know why I'm writing this all out again. All right, why did I do this? Well, I'm committed. Okay, so that's the original limit, but I really become a one-dimensional limit. Now it's just t. Everywhere where I see an x, I put 0. Everywhere I see a y, I put t. So I get 0 squared times t over 0 to the fourth plus t squared. Well, that's the limit as t goes to 0 of 0, which is 0. Okay, so vertically, we go to 0. No surprise there. You want to do vertical, but sorry, we said vertical. You said diagonal. I'm not just going to do any diagonal line. I'm going to do every diagonal line, all simultaneously. How am I going to do all diagonal lines simultaneously, you ask? Well, I have something up my sleeve. I'm going to look at the following parameterization, where it's going to be of the form t comma k times t. And all I'm going to say is that k is just a number. So k is some fixed number. All right, so I have k is some fixed number. Now, what number? Well, it depends on the slant. So what is this really parameterizing? If you look at what this is parameterizing, this is the line y equals k times x. So I'm coming along y equals k times x. And I want to say, well, what happens if I come along y equals k times x? So along a diagonal, what do we get? Well, it's going to become the limit as t goes to 0. So let's just work it through. I have x squared, t squared, times y, k times t, divided by x to the fourth, t to the fourth, plus y squared, which is k squared, t squared. That's all true. Now, what can I do next? I can do some cancellation. I can cancel some t squareds. So this becomes the limit as t goes to 0 of kt divided by t squared plus k squared. What does that do when t goes to 0?
0.
It goes to 0. Now you might say, oh, wait a second. Are you sure? Yes. You should be a little bit careful, because there's now two possibilities. What if k equals 0? Let's just, on a side note, k equals 0. So we actually were coming in straight horizontal. If k were 0, what could we do? Well, if k were 0, what's the numerator? It's 0 over t squared. Well, look, that means it's really just the limit as t goes to 0 of 0, which is 0. And if k is not 0, well, what happens is plug in t equals 0, you're going to get 0 over k squared, which is 0. So what does that mean? What have we shown? We've shown the following. No matter which direction you approach the origin, you are always going to get 0. From every single direction. Every single one. We've done them all simultaneously. Cool. What's our conclusion? And again, every direction we've approached, we always got 0. What can we conclude? We don't know. We don't know. Now, what do we know? It might exist, because we've always gotten a consistent answer. If it does exist, what's the answer? 0. Are we sure yet if the answer is 0? No. Now, you might say, I'm pretty convinced, because I've seen you go in every direction. But remember the picture here. This method is only useful to show limits don't exist, and in particular, what haven't we done? We haven't done interesting directions. We've always come on straight lines. So now we're going to do an interesting direction, and this will sort of be like a, where did this come from? And the answer is, I've done it before. Okay. But it's not so far off. It's not too crazy to think, well, what was happening before, if you think about it, is we kind of got the powers to match. So for example, we got like t squareds over t squareds. We'd like the powers to match again. And if you see how it's x to the fourth and y squared, well, you'd say, what if I made y x squared? So it's like x squared squared, then we'd have like x to the fourth. So here's what we're going to do. We are going to approach not on a straight line, but on a parabola. The parabola y equals x squared. Now the parameterization for this is t comma t squared. So if I approach on a parabola, what happens? Well, it's a limit as t goes to 0 of, what's the numerator going to be? Well, so everywhere you see an x, you put t, so t squared. Everywhere you see a y, you put t squared times t squared, divided by x to the fourth, so that's t to the fourth, and y squared becomes t to the fourth. So that's the limit as t goes to 0 of what? A half. What's that limit? 1/2. And what do you notice about a half and 0? They're not the same. So what's the conclusion? Does not exist. Whoa. That's kind of unexpected. Just limits can be tricky. Limits can be tricky. All right. Well, running short on time. So we're going to fly through this next one. So the next strategy is to use squeezing. Now, squeeze says what? Well, when you're squeezing, I want to say let's bound it above and below by two things which are simpler. And now, if I can bound it above and below by things which are simpler, then I can say what happens to those simpler things. If they go to the same point, I'm done. Because I'm squeezing the answer together. So here's a quick example. Limit as xy goes to 0, 0 of x to the fourth over x squared plus y squared. Well, it goes to 0 over 0. Now a little bit different though. Notice how the power upstairs is quite a bit larger. X to the fourth. So you should anticipate, the intuition says that should be going to 0 faster than an x squared or a y squared. So somehow the numerator should go to 0 a lot faster. And we want to exploit that. So here's how we're going to think of it. We're going to think of x to the fourth as x squared times x squared. Now, the reason I want to do that is because I can say that the x squared is really comparable to the x squared. Everyone agrees on that. In fact, we can say the following is true. It's very easy to check this. As long as I'm not at the origin, x squared over x squared plus y squared is always greater than or equal to 0. Because all the terms are positive. The square does that to you. It's also always less than or equal to 1. Now that one might take a second to think about. Why is x squared over x squared plus y squared less than or equal to 1? Because the bottom has to be at least as big or bigger. If I have a fraction and the bottom is as big or bigger, then it can't be bigger than 1. So multiply everything by x squared now. 0 is less than or equal to x to the fourth over x squared plus y squared, which is less than or equal to x squared. Now we say, aha. As I get close to the origin, what does 0 get close to? 0. As I get close to the origin, what does x squared get close to? 0, because it's a polynomial. And if it's a polynomial, you plug it in. And this has to get somewhere in between 0 and 0. Well, what's left? What's in between 0 and 0? Only 0. It's forced to say that that limit is 0. So the limit exists. Now, that's strategy number 3. Strategy number 4, take more math classes. Well, that means look for techniques. Now, you might say, you seem really excited to get people to take more math classes. And the answer is, yes, I'm very excited to get people to take more math classes. You see, we have this little punch card here. And if I can make 10 students into math majors, I get a free sandwich. And I'm only 3 away. So anyways, so that's the last strategy. We'll start again next time.